Hello and welcome to part 2 of Anatomy and Physiology for the urogenital system. Today we're going to be continuing to look at some of the key principles of the urogenital system by taking a look at renal function and homeostasis, as well as the bladder, urine and fluid balance. So let's start by taking a look at renal function and homeostasis. So the kidney has several roles, but the main function of the kidney is to maintain homeostasis for a number of solutes and water. And homeostasis is normally maintained despite variations in endogenous production in terms of how much we produce of a substance and dietary intake, or how much we take it in for our food. So homeostasis is maintaining total body contents at a stable and normal level even if the phase of changes in dietary intake or endogenous productions change. So what do we have to maintain through the kidneys? Well, first of all, it's our electrolytes, so sodium, potassium and chloride. Our water, so our osmolarity. Our acid-base balance, so bicarbonate and H+. Minerals, so calcium, phosphorus and magnesium. And waste materials such as urea, creatinine and uric acid. So what are these waste materials and where do they come from? So protein is broken down into urea. Muscle gives off creatinine as a waste product. And nucleic acids break down into uric acid. And these are waste materials that can be measured either in the blood or elsewhere in order to give a reading of how well our kidneys are working. So moving on from this, the kidney also has endocrine functions. In other words, it produces hormones. So the hormones that it produces are erythropoietin, and this aids in red blood cell production. It also aids with the formation of the active form of vitamin D, and renin production as well from juxtaglomerular cells. In addition to this, it also has paracrine and autocrine functions with the production of bradykinin, prostaglandins, endothelial factors such as nitric oxide and endothelin. In addition to this, the kidney is also responsible for maintaining our blood pressure regulation, and it does this through homeostasis of sodium and water by maintaining normal extracellular fluid volume. As you may know, there are several ways we can maintain blood pressure in our bodies. However, this is one way, and it's the maintenance of sodium and water levels. So for example, if we reabsorb a high level of sodium into the blood, water is going to follow because the osmolarity of the blood will have decreased, and therefore water will travel across into the blood as well and increase extracellular fluid volume. And if there's more volume in there to pump around, then the blood pressure is going to increase, and vice versa that as well. And it does this by the use of the renin-angiotensin-aldosterone axis, or the RAAS system, and we'll go through this a little bit more in a moment. It also produces vasodilatory substances such as nitric oxide, which can help to reduce blood pressure by causing vasodilation. So the other roles of the kidney include catabolism, so breakdown of small peptide hormones such as insulin, production of glucose via gluconeogenesis during fasting, and elimination of many medications, so changes in our kidney function would also alter our plasma concentrations of any medications that the patient may be on. As well as that, it also aids the filtration of blood before it returns back to the heart. GFR is a term you need to be aware of, and it's the glomerular filtration rate, and it's a test we use in order to check how well the kidneys are working, and specifically it estimates how much blood passes through the glomeruli each minute. A blood sample is taken and sent to the lab, and in the lab the creatinine level in the blood is tested. And creatinine, as we said before, is a chemical from the breakdown of muscles that the body makes to supply energy. And the lab specialist combines the patient's creatinine level with several other factors to estimate their individual GFR. Normal results for GFR tend to be above 90, and we can graduate as this decreases. We can term this chronic kidney disease in terms of how much the GFR has reduced by. So it's a good measure of CKD. Bear in mind as well that older people will have naturally lower GFRs because GFR naturally reduces with age, and so maybe you wouldn't be as worried if an older person's GFR was lower than a younger person's. So the clearance ratio. Clearance is a general concept that describes the rate at which substances are removed, i.e. cleared, from the plasma in the body. And renal clearance of a substance is the volume of plasma completely cleared of a substance per minute. It can be very difficult to measure this clearance of a substance directly, so instead we use other substances from the body that we know are freely filtered to give an indication of how well the kidneys are working. And we do this through the equation clearance equals urine concentration times urine flow rate divided by plasma concentration. So commonly we use things like inulin or creatinine because these are both freely filtered. Having said this, we tend to use creatinine more because inulin has to be injected into the patient, whereas creatinine is already there from muscle breakdown. However, we must take into account what patient we're dealing with. If we're dealing with a 20-year-old bodybuilder, we're going to see a different clearance of creatinine than we are a 70-year-old frail woman, because naturally the 20-year-old bodybuilder is going to have greater levels of creatinine already due to having greater muscle breakdown. Inulin is a more accurate indicator of GFR than creatinine, but like we've already said, it requires an infusion, so it's less commonly used because it's more invasive. So how can we interpret clearance ratios? Well, if someone's got a clearance ratio of 1, then the solute is handled exactly the same as inulin, and its renal clearance is equal to GFR. If the clearance ratio is smaller than 1, then the solute is filtered by the kidneys, but it's also reabsorbed, so for example sodium. And if the clearance is greater than 1, then the solute is filtered and it's actively secreted from the peritubular capillaries as well into the tubular fluid, such as potassium. And finally, if your clearance ratio is 0, then either the solute is too large to be filtered, such as a protein, or it's filtered and 100% then reabsorbed. So for example, glucose is filtered, but then it's all reabsorbed back into the blood normally. And therefore you wouldn't really normally expect to see glucose in the urine. And therefore if you do get traces of glucose in the urinalysis that you may perform on a patient, then you should potentially be suspecting things like diabetes in this patient. Moving on now to take a look at the bladder, urine and fluid balance, and urine formation. So there are 4 steps to urine formation, and these include glomerular filtration, tubular reabsorption, tubular secretion, and excretion. Now the last stage is fairly self-explanatory. However, the first 3 we'll go into in a little bit more detail. So first of all, we have glomerular filtration. So as blood flows through the glomerulus, blood pressure pushes water and solutes from the capillaries into the capsule through a filtration membrane. And inside the glomerulus, blood pressure pushes fluid from capillaries into the glomerular capsule through a specialized layer of cells. And this layer, aka the filtration membrane, allows water and small solutes to pass, but blocks blood cells and large proteins. So those components, the larger proteins and the blood cells, remain in the bloodstream. The filtrate, i.e. the fluid that's passed through the membrane, flows from the glomerular capsule further into the nephron. And we can see this.
The filtration membrane blocks blood cells and large proteins, but allows water and small solutes to pass.
So after glomerular filtration, we can have tubular reabsorption, and with thanks to visible body for the videos that we're using here. So the glomerulus now filters water and small solutes out of the bloodstream, and the resulting filtrate contains waste, but also other substances that the body needs, such as essential ions, glucose, amino acids, and smaller proteins. And when the filtrate exits the glomerulus, it flows into a duct in the nephron called the renal tubule. So as it moves, the needed substances and some water are reabsorbed through the tubule wall into adjacent capillaries. And this reabsorption of vital nutrients from the filtrate is the second step in urine creation. So here we can see this in action.
Nutrients pass through the renal tubule back into the capillaries. Here the body reabsorbs what it needs and creates urine.
So the third stage of urine production is tubular secretion. So the filtrate absorbed in the glomerulus flows through the renal tubule, where nutrients and water are reabsorbed into capillaries. At the same time, waste ions and hydrogen ions pass from the capillaries into the renal tubule, and this is secretion. So the secreted ions combine with the remaining filtrate and become urine, and therefore this urine flows out of the nephron tubule into the collecting duct, and so forth out of the kidney and out down the ureters. And you can see this here.
Ions and hydrogen ions pass from capillaries into the renal tubule. This creates urine, which passes out of the kidney into the ureter and down to the bladder.
And so finally we can excrete the urine. So urine passes through the collecting ducts to the renal papillae, to the minor and major calyces, and out down the ureters to the bladder. And from the bladder it passes through the urethra and out of the body. So if we think about what makes up our urine, The composition reflects the quantities of water and solutes that the kidneys must eliminate for the body to maintain homeostasis. So for this reason, our urine is normally 95% made up of water, and also has urea at about 2%, uric acid, trace amounts of amino acids, and electrolytes to build it up. Fluid balance is largely dependent on the renin-angiotensin-aldosterone system, and this contributes to blood pressure as well. So, for example, the liver produces angiotensinogen, which is acted upon by renin, which is released from the juxtaglomerular cells of the kidney due to response in a decrease in renal perfusion. So not enough blood getting to the kidneys, the juxtaglomerular cells secrete renin, which acts on angiotensinogen from the liver. This produces angiotensin-1, which is acted upon by ACE, angiotensin converting enzyme, which is released from the surface of the pulmonary and renal endothelium. This creates angiotensin-2, and angiotensin-2 carries out a variety of actions. So it increases sympathetic activity, so already increases vasoconstriction, which increases blood pressure. It also increases tubular sodium chloride reabsorption and potassium excretion, which leads to more H2O retention. In other words, we keep more H2O in the blood because we're keeping more sodium and chloride in the blood, and therefore this increases our extracellular volume, and therefore this also increases blood pressure, in combination with vasoconstriction and aldosterone secretion, which also contributes to this electrolyte reabsorption. Overall, we have a vast increase in blood pressure. As well as this, we also have ADH secretion, which means we have more H2O absorption from there, again contributing to an increase in extracellular volume. So renin-angiotensin system is really important. Renin is released, as we've already said, from the juxtaglomerular cells in the kidneys due to three things. Firstly, a drop in blood pressure. Secondly, due to sympathetic stimuli. And thirdly, due to macular denser cells sensing a decrease in chloride, potassium and sodium in the blood. The aldosterone causes the kidney to conserve sodium and excrete potassium. So aldosterone is released from the adrenal glands due to low blood volume, and it causes water conservation of the body due to increased reabsorption of sodium. With regards to bladder, the bladder is stimulated, both involuntary and voluntary, so it's parasympathetic and sympathetic input. So our parasympathetic input excites the detrusor muscle. It leads to the detrusor muscle contraction, and it's active during micturition. In other words, it's active during urination, causing us to pee. So PP. SS, sympathetic store urine. It leads to contraction of the internal urethral sphincter. It relaxes during micturition, and it's active during the storing of urine. So the internal urethral sphincter is a smooth muscle and under involuntary control. We can't do anything about that. It's parasympathetic, sympathetic control. However, lower down we have the external urethral sphincter, and this is under skeletal muscle, so voluntary control. And therefore we can choose to a degree up until when we excrete urine, when it's socially acceptable. In terms of voiding and knowing when to void, the contraction of the detrusor muscle and relaxation of the external urethral sphincter is what causes voiding. And distension stimulates stretch receptors in the bladder. Impulses are sent to the detrusor muscle from the central nervous system, and as bladder fills up with urine, the internal pressure increases and forces the sphincter to open. A second reflex relaxes the sphincter unless voluntary control maintains its contraction. In other words, if it's not socially acceptable to void. And that's everything for this video. Thank you very much for listening. If you do have any questions, please feel free to get in touch. Thank you very much.